Hello everyone, welcome back for the afternoon session. Our first speaker for the afternoon is Professor Marc Cutkosky from Stanford.
Okay, good afternoon everybody. It's really my pleasure to kick off the afternoon session. I want to talk today about hands and feet. And the interesting thing is that when you're using feet for climbing, it's pretty much the same as hands. It's all about controlling contacts and internal forces, which means, of course, you have to do tactile and force sensing, which also means that you want to use compliant structures and materials to help you do a better job of conforming and controlling those forces. And these are themes that are going to come up. I don't have time really to talk in detail about any of this, but I wanted to show you some recent work we've been doing on hands and feet. So we've been involved in some hand projects lately with under-actuated hands. And when you look at the spectrum, there is a number of them ranging from very compliant and conformal ones like the Hirose's hand on the far left to ones that have rigid links, but they're under-actuated so they can close around an object and then they hold it precisely. And then we've been working on a couple that are kind of in the middle, like the arm-H hand. And in particular, I'd like to just touch on three that we've been working on. The first one is with Hannah Stewart, who's in the audience there, and Sichuan, also working with Oussama Khatib. Now, Oussama's already told you about the robot, and we've been trying to convince him that he should call it Ariel, but he wants to use an acronym, so you can help us. And I'll tell you a little bit about that hand. Also, the arm-H hand that we did with SRI and Mecca. And then the last one on the right is a hand that we have been working on with JPL for their entry in the robotics challenge for DARPA. And this, interestingly, they call it RoboSimian. It's sort of an orangutan robot, and the hands are feet. Okay, so the approach we've been taking for our hand design is to do fast simulation at low speed. It's a huge search space, how many fingers and what the properties of them are and so forth. And we want to include important things like friction and joint limits and so on. So we do that. We were able to build up regions of things like under what circumstances can this hand successfully grasp an object? What is the effect of changing different finger stiffnesses? How much force can we resist if we pull out in different directions? And I'll just show you a couple quick examples. This is the arm-H hand on the right. And one of the interesting features of it is that it has electrostatic brakes, which are shown down here. They're laminated layers put up at a high voltage so that they squeeze together and they lock the joint. And brakes are nice because they're much more compact than motors for the same torque. And it allows us to have a single motor for each finger and yet still have some of the dexterity that you might otherwise expect from a fully actuated hand. And what this video is showing is the ability to grasp first by releasing and then locking up the brake so that it sucks that object right in. The next slide I want to show is a hand that Hannah's been working on with a couple of other students. We have Sichuan has been working on the modeling. Uses flexures because it's easier to make them waterproof. And what the modeling is showing is the advantages of having a kind of a non-constant geometry of the tendons so that we can get the fingers to curl in. The other thing that turned out to be a big help with this hand is adding suction. When you're trying to grasp something underwater, the motion of your hand pushes a little bit of water ahead of it, which tends to push away the very object that you were trying to grab gently. But if you pull a little bit of suction, this is not like an octopus sucker. It doesn't require making a seal. Just a very gentle suction, it can make all the difference in terms of being able to grasp soft and slippery objects. You can see it here, that the soap bar is just a lot easier to grab with a little bit of suction. So feet is almost the same thing. Once again, they're under-actuated. They have to conform to surfaces. They have to distribute forces. And in just a couple minutes, I want to say a word or two about that. Even the gecko has to worry about controlling internal forces. That's why when they're going head first downhill, they have to turn their feet backwards, or otherwise they would fall off. So what we've been doing most recently with adhesion is what I call dynamic surface grasping. And my inspiration here is the Coligo, gliding and grasping a tree. And we've been working with a number of investigators, Vijay Kumar's group at UPenn, and most closely with Sean Humbert at Maryland on trying to get quadrotors to land and perch on walls and ceilings. So their problem is to control the quadrotor in phases 1 and 2. Ours comes in phase 3, the final stages of this flight. As soon as you make contact, those forces really dominate the dynamics. It's very fast. It's about 50 milliseconds. And so we need mechanisms that will let us align the quadrotor and grip. And here's just a quick video of one. It's too bad I need this. I should show you the sound because it sounds like an enraged mosquito. It's okay. Never mind. There we go. And the only thing I don't like about this video is it makes it look easy, like the thing just has chewing gum on its head. But actually, it's a fairly complicated process. We come in, we may be misaligned, so we have outriggers to align, and this means we want a small polar moment of inertia. We absorb the excess kinetic energy. We use that to compress a structure internal to the mechanism. That's what loads the adhesives and then allows these adhesives to grip. And then at the end, we have a little latch. We release that, and we have enough energy to pop off, and you can start flying again. Doing a lot of work with dynamic modeling, verifying that these things will grip under the circumstances that we predict they will, and also just trying to make that envelope bigger. And in particular, let's look at this part of the envelope in the upper right. That's adhesion failure is one of the modes. And that really requires looking in some detail at what the adhesives are doing. So we have two opposed pads here, and we're pulling on them with tendons, and that means that we have a kind of a limit curve, which is shown by the blue empirical dots, that the range in which we can pull forces and still sustain the contact. And as you can see, the limit in the best case is around 2 newtons for this little gripper. And that has interesting implications for the springs. It turns out that it means that there's a big reason to use nonlinear springs to get sort of maximum energy absorption in a tight space. And there's not going to be time to go into detail on that. But the point I just wanted to make is that there's that 2 Newton limit. And you can really see the benefit you get of having a spring that goes up and then has a nearly constant force. So there's a lot more energy under the curve. And that makes a big difference. Okay, let me finish with one last thing. How do we grasp objects in space? So we have a big problem with space debris. There have been satellites destroyed by space debris. There's the movie Gravity that just came out, in which that plays a role. When I first heard about this, it sounded like science fiction, and I vaguely remembered that there was a James Bond movie in which the bad guys had come and indeed they had grasped an object in space. What we would like is something a little less cumbersome and ferocious looking than that. The idea is that you have a satellite with an arm and with, again, some of these gecko, I don't know, are they feet or hands, whichever, that grasp the object and allow you to reel it in. And I should also point out that Allison's group is working in this, and so we've been collaborating a bit with them as well as with Aaron Parness at JPL on space gripping. And this is the last slide. The real trick is that you want to grasp things with very low force because just like trying to grasp the things underwater, you don't want to push them out of the way. So here they are in space. You want to latch onto that surface and grip it. You can't push it because then you just send it off into another orbit and then things are worse than ever. So grabbing with very low effort is an important thing, and this is how demonstrating a low effort gripper. All right. Thank you very much.
Okay, so our next presenter is Steven Peters from the Open Source Robotics Foundation.
So what I'm going to focus on today is trying to maximize buzzwords. I've opted to go for buzzwords instead of acronyms, so that was my strategy today. But seriously, I'm going to talk about some of the work that we're doing on open source software that focuses on robotic simulation and specifically using cloud infrastructure. And this is our logo. This is our fun logo at Open Source Robotics Foundation. And then this is just a video of one of the competitors in the DARPA's Virtual Robotics Challenge. This is a challenge that's focusing on increasing the use of robots for disaster response. And a cool thing about this DARPA challenge was that it was all cloud-based, or all Yeah, so it was in the cloud using open software, specifically the Gazebo simulator and ROS. This is an example of one of the walking tasks. This is a team that they fell over, but they were able to get back up. This robot is the Atlas robot from Boston Dynamics. It's a humanoid. It has a variety of sensors on the head. There's laser and stereo vision. And then it also has some hands that Morgan has worked on. This is just a rendering from some of that. There's a nice rubble pile up there to avoid. Another one of the tasks from the VR, from the challenge, was a manipulation task. And the goal for this, as one of the earlier presenters mentioned, is for disaster response, and specifically using humanoid robots, because there's lots of places that were designed for humans, to go into, like technicians and things. So they pick up the hose and connect it. I'm going to skip through because I'm going to do a live demo. And this is a fun one. We hear a lot about robotic cars, but here the task was to put a humanoid robot inside of a car and drive it. Right. It's probably the easiest way to do it. No, but the idea is that if you're in an emergency situation and there's specialized vehicles that you need to use. This is how I get into my car. I don't know about you. Say there's a fire that breaks out. That's a time critical situation. And say you have a water truck. It's not an autonomous water truck, but you'd still like to be able to, if say there was radiation as well. There were a lot of fires at Fukushima, so firefighting is one of the things that they were focusing on. So that's kind of the justification for this type of thing, even though it seems a little silly. It is cool, but it's also potentially useful. So this is these are some scenes from the VRC, the Virtual Robotics Challenge. And now I'm going to talk a little bit about Gazebo, which is the simulator. That's what I work on. So one of the things that I'm working on is adding support for more physics engines. It initially used Open Dynamics Engine. We're adding, there's a single bullet point because we have partial support for bullet physics. We're also adding support for SimBody, which is from Stanford, and DartSim, which is from Georgia Tech. Now, key buzzwords for the physics engines is using Featherstone's algorithm, which can give much more accurate solution of the constrained rigid body dynamics. And also regression tests. We're putting in tests to verify that all the physics engines are working properly and that they all have the same interface. Traditionally, you've needed Ubuntu with a GPU to run Gazebo. We have partial support for Mac, which I'm going to demonstrate right here. Whoops. Okay. Let's see if we can full screen that. Okay. So this is just, I see this all the time, just an array of double pendulums swinging around. It's pretty normal. And in your scientific quest for knowledge, sometimes you just have to try things out. Morgan wrote this script. There's a car. I think, yeah, that's good. But what about the context? Can this simulate real-world environments? Yes. Gas station. So yes, we have partial support for Mac OS right now, which is the point of that. And now I'm going to show you a demo of our cloud, some of our recent cloud interfaces, which are very cool. So because using Ubuntu, using these high-power Ubuntu machines, not everyone has them and so forth. But with the cloud, you can get a machine. Can't talk and demo at the same time. Whoa, that's not good. That's not good either. Okay, we'll approximate it like that. So what I have here is we set up an Amazon machine to run the simulator, and then we can connect to it. This is in Chrome using a browser. It's a little laggy. Come on, Air Bears. Help me out here. Well, I'll switch over to the Python dashboard, which is pretty cool. This is what you get when you do a live demo. I should have stuck with the dumpsters. Okay, I'm sorry, folks. What the other thing that I was about to show was an IPython notebook, which is a place. In your browser, you can run Python code. You can also run shell commands. So you can test ROS code on a robot simulated in the cloud. You can get camera images. You can send it commands like start walking or things like that. Yeah, I'll just end there. But I'll say. We're working on open source software for robotics using Gazebo, interfacing with ROS, and we'd love to, work with people. So, thanks.
Our next presenter will be Professor Francesco Borrelli from Berkeley.
Okay, I'll try to be short. 4 minutes on people that don't know me, what is my lab doing, and for people that know me, what is the most coolest thing in my lab. So we study predictive control. So very simple idea. You want to control a trajectory of a system. You have some regions you want to avoid because of the inertia of the system, because objects are moving. You want to make a forecast. Otherwise, you will instead of follow the green trajectory, you follow the red trajectory, and you crash with the obstacle. So the most simple mathematical formulation of this is you have a dynamical system, which has a state. You have a control over certain inputs, and there is environment and humans around you that you don't control. So at time t, you want to decide which control action to take based on forecast of the environment and the humans around you. Okay, so there's predictions in there, and the conjecture is that because of the inertia, because of the dynamic scene, without predictive control, you are not able to solve complex tasks. So this is my first message: is the choice for model-based systematic control of complex systems. And if you do not believe it, this is a study we are doing with jugglers. This is by the way, Pete, I look forward to see a robotic juggler. This is a simple task, 3 balls the same, okay? Real speed, right-hand side. We give the juggler different objects, and you can see that he can't use his peripheral vision anymore. He has to track the object, and the point is that this is a very good juggler. The only reason why I can solve this, and the main difference with a bad juggler can do only this, is because of forecasts. So if you click here, this has always been conjecture. We can study now. You see there where you're pointing is actually where the ball is going to be, right? And that's actually the main reason why you can solve this complex task. Okay. Moving forward, what do we study in my lab? What is a good model abstraction for doing predictive control? What is the effect of your forecasts? Your uncertainty about the future belongs to given set. You have probability distribution functions, and you want to understand what is this effect in feedback, and how do you design a predictive controller. I'll spend 1 word about this. The simplest formulation, I don't have a pointer here, but you basically are looking for a set of feedback policy over an horizon, pi 0, pi 1, pi n, that minimizes certain costs, respect your system dynamics, and satisfy your state and constraints. Okay? So the simple predictive controller, receding horizon controller, look-ahead controller is basically simple, is telling you, take your state, apply your first feedback policy you have found, this will be your best action, and repeat and resolve the problem again. Okay? So second message for today, this simple concept, and many of you have seen in one form or another running this, can be implemented in works. Okay? Today, for instance, if you have a simple steering control problem, you want to steer and apply differential braking to a vehicle, and you have a bicycle model, you have uncertainty about the longitudinal speed because the driver is acting on it. You have uncertainty about the driver steering, so you have an additional action on top of what the driver is doing. You have nonlinearities coming from the nonlinear tire curves of the vehicle. What you can do is to approximate them, write down a set of piecewise affine differential equation, and if you have the right tools, in a couple of hours you end up with a predictive control algorithm that does this maneuver here, which is very difficult. So the driver thinks it's actually steering, going high speed on ice. Really, is doing this only because of the controller. So he only sets his control input, but actually the controller, if there was a camera looking at the vehicle, the wheels are counter-steering, are going in the opposite direction. Okay. This works also on self-driving cars. I'll spare you the nth video on self-driving cars. What do we, summarizing, for people that know me, large scale, we study predictive control, and my lab focuses on large scale system, uncertain prediction. You will hear from Theresa about human-machine interaction, constraint satisfaction, real-time implementation. What is new? I want to tell you a few words about real-time implementation, so fast optimization in real time. This is the general problem we want to solve. And in general, it's very complex. Okay, many of you have tools for tricks for making this faster. So the simplest trick is actually to say, instead of looking for all possible feedback policy, I'll select a specific class of feedback policy, maybe a special trajectory, polynomial trajectory, linear gains, and so on. The second one is that, enforcing the constraints that the state is in a certain region for all possible uncertainty stuff. And so what you do, you relax this constraint and you allow the probability of violation to be small. Okay. The third one is that to make this faster, you can actually exploit the solution of the resulting optimization problem. Meaning, from here, you end up with a nonlinear program where you have to look for a variable that minimizes your cost subject to your constraints, and the state that you update in real time is a parameter. And so what we're doing is trying to study ways of making these problems faster. Okay. One way you can download from the web is BLOM. BLOM stands for Berkeley Laboratory for Optimization Modeling. It's work of Anthony Kellman, Jason, and Sergey. From Simulink, if you have your dynamical model, you can put your constraints, your cost function. With the click of a button, it generates a predictive control that you can download on your embedded platform. Okay? So BLOM, you can use BLOM, has many interesting things in there. I'll skip this. And the third message for today is that if you ever want a fast nonlinear predictive controller for a large-scale system, try to use BLOM. It actually works really well. We have tested this under thousands of variables, solves problems in the order of minutes. Okay? What if we have sampling time faster than minutes? This is my last message. What we have done here is to plot size of a problem versus the time it takes at each time step to solve, as reported by a few papers in the literature. Okay? And the idea was not to compare them, because each one of these is different. Up there is BLOM, hundreds of thousands of variables, and we solve nonlinear optimization. Around here, there is a fast gradient method from Boyd. This is for QPs. So the idea was basically to show you that if you want to be fast, one possibility, there is a limit. This is all digital computation, is to go here and do analog computing. So this is the last message. What does analog optimization mean? It means to design an electric circuit which a steady state, once you make the voltage, correspond to the solution of an optimization problem. So this is a linear program. You want to solve for a set of V's that minimize your costs subject to equality and inequality constraints. And I'm saying that you can put together a circuit You apply a voltage to this circuit, you let it go at steady state, and the solution, once you measure the voltages here, the solution will be the solution of this linear optimization problem. Okay? So why we do that, there is a paper on the web you can download. This is recent work. It's very interesting and simple. The resistance are here. The resistors are a function of your equality and equality constraints. The circuit, the idea is that your forecast, your state, enters the right-hand side of the constraints, and you do this by just changing the voltage to this circuit. Okay, and the neat thing about this circuit is that it only has resistors and diodes, okay, and external sources. So why this works and how it works, I'll skip. But the idea is that once you write down the equilibrium point of this circuit, these are the KKT condition of a linear program. Sergey has been working on this for the past 2 years. There was a work in the 60s about analog optimization at Berkeley. The circuit was too complex. It was very difficult to implement. What we have been doing, basically, the circuit that Sergey has designed is much faster and simpler in the past, and it basically extended to solve it also quadratic programs. Final message today is that if you want to solve a fast linear quadratic program in the order of nanoseconds, you can use an analog circuit. These are results with SPICE, linear program with 10 centimeters wire, 200 nanoseconds if you have 100 variables. There's a predictive control there to the right-hand side. If you go now on 45 nanometer CMOS, then you can have a 10 variables linear program solving in order of 5 nanoseconds. Okay? If you have a linear program or a quadratic program you want to run fast for your robotic application, be happy to hear to design a circuit for you and test it. This was my last message. The future of computation will be mixed analog digital, and as any prediction has a probability less than 1 to be true, so maybe. So this concludes my talk. 4 main messages. We study predictive control. It works, and if you have a large-scale nonlinear problem, try to use Blom. If you have a small, very fast optimization problem, talk to us. Maybe we can design an analog circuit, and Theresa will talk about more interesting work on the human side. Thank you.
Our next presenter is Sanghyun Hong from UC Berkeley.
Hello, I'm Sanghyun Hong. I'm talking about predictive semi-autonomous vehicle with parameter identification. We have 3 parts in our project. One is a design of a controller, and the other team is about driver modeling, and the other one is parameter identification. So final goal of our project is to provide better control based on the information of human driver and vehicle parameters. Okay, so I mainly talk about controller and parameter identification. The controller design team made a lane keeping system which can also avoid an obstacle simultaneously. So they combined steering and braking for control input to correct the driver's steering. And they use model predictive control technique so that they can predict the future motion of vehicle. And they also incorporated the driver model in predicting the vehicle's motion. So at the bottom, you can see the simple driver model. It's based on the information of the prediction of the drivers is represented by their steering angle, which is delta D at the bottom, which is calculated with a combination of the distance of vehicle COG to the center line of the road. And the second factor is the error of vehicle orientation with respect to the road tangent. This is the latest testing video. So the first video shows the lane keeping system on the straight lane. We went to California Proving Ground to test this controller. And the second video is on the curved road. As you can see here, the vehicle is staying within the lane. Okay. The other team is working on the vehicle inertial parameter identification. Vehicle inertial parameters such as sprung mass and yaw moment of inertia and position of COG can vary under the different operating conditions, such as the different number of luggages and passengers. So we want to estimate these inertial parameters, and we made some algorithm. In estimation algorithm, we use unscented Kalman filter, and we adopt the dual estimation architecture. And we also want to use only the already commercialized standard vehicle sensors. So we use only lateral acceleration and vehicle velocity and yaw rate and longitudinal acceleration. We don't use any advanced sensor such as GPS. We also tested this algorithm at the Richmond Field Station. We followed the blue colored track for 500 seconds, which is 3 laps. So as you can see in this plot, we can see pretty good convergence. In the plots, the vertical, in the estimation, we estimate the sprung mass when going straight, and then we estimate the position of COG when driving on the curved road. So the vertical lines represent the time instant when the estimator switch on. Okay, that's all.
Our next speaker is Advait Jain from Redwood Robotics.
So I'm Advait. I'm currently with Redwood, but for the most part today I'll be representing Mecha Robotics, and I'll be talking more about research, less about manufacturing. Main idea here is that if we want to productize academic research, having close collaborations with small companies is really useful, and small companies is key here. The example is collaboration to try and get human-friendly collaborative robots from research to product, and the company involved here is Mecha Robotics. This was founded in 2007 by Aaron Edsinger and Jeff Weber. And in their words, the core value for this company is innovative engineering and beautiful design. The images on the right are their product line specifically for research. So it's compliant arms, dexterous hands, expressive heads, mobile manipulators, but all these are geared towards what research labs want. In addition to this, what Mecha as a small company is able to do is customize their products to the specific needs of different research labs, whether it's building on their expertise with series elastic actuators to make an agile biped or adding specialized sensors that you might need. And I'm probably the third person now to have a rendering of the Red Sea project, and I'll talk more about it in just a little bit. So now I'll walk you through a number of different examples of how academic labs can collaborate with small companies. Here's the simplest example. Academic labs can actually provide bootstrap financing for these small companies. As an example, Mecha got started when 2 labs at Georgia Tech, one, the Healthcare Robotics Lab, which is where I did my PhD research, and the Socially Intelligent Machines Lab, they provided an advance payment so that we could get these arms. And that really helped take Domo, which was Aaron Edsinger's PhD thesis, productize it, and give these 2 labs at Georgia Tech arms that we could then use for our research. And this is different from other examples that we've seen today in that Domo was not ready for venture capital. It's not a product, but it's something that academic research really needs to get started. And then another example is let's collaborate and make integrated systems. So again, from Georgia Tech, we got the arms from Mecha, we put it together into a mobile manipulator in close collaboration with Mecha, and then Mecha turned it around and delivered a new research product, which is the Mecha mobile manipulator. Here's the Red Sea project, which is ongoing, work with between Mecha, Oussama Khatib, and Marc Cutkosky. And here again, Mecha is customizing their arms so that they can fit on a submersible and can be used underwater. Another example is a lot of research labs are focused on software and systems. Certainly was the case for my lab. And we need new sensors to do our research. Example being here, whole arm tactile sensing. That's not common right now on robots. That's not something that a lab that focuses on software does, but it's really useful for the lab itself. And this is where Mecha filled in a role that research labs really cannot do. So Mecha took research from BDML, which is Marc Cutkosky's lab, which is a proof of concept design for a tactile sensor, productized it, worked with Georgia Tech to make software drivers, and then really delivered us the sensor that we could use in our research. Now, without Mecha sitting in between these two academic research labs, the technology couldn't really have flowed from one to the other. Now, again, wearing my researcher hat, this truly is just the beginning. Everything that we've shown, all the software needs to be tested with more people in more environments, with more robots. Everything from sensors to robots to user interfaces can be faster, simpler, smarter. And we'd really like to kick off the next generation of robot hardware, whether it's cost being reduced, whether it's making them more compact, lighter weight, having better sensors. And that's where companies like Redwood and others can sort of come in. Just one slide on Redwood. 3 founding companies for us, Mecha, Willow Garage, and SRI. And it's really, again, taking this idea of human-safe arms that can work next to people and moving it from research, which is Domo on the left, through the Mecha products, which are specifically for academic research labs, to something that can be used by the industry for manufacturing. So that's it for now. Thank you.
Our next presenter is Arjun Singh from UC Berkeley.
Cool. All right, so today I'm going to talk about a data set we're collecting. It's a large-scale 3D data set of object instances. But first, I'll talk about how computer vision kind of works today. So you train and test on data sets that are essentially collected from the internet, like ImageNet, and you kind of search the internet for images, you categorize them, and that's the data set. And there's been significant progress on these data sets using methods like deformable part models, deep learning, and many more. And kind of good performance on localization of objects in these data sets is kind of like 70% or 60% or something like that. However, these methods aren't directly applicable to robotics. So why is robotic perception different from traditional computer vision? So one key thing is that you need nearly perfect performance. So 70% is definitely not good enough. And as Kurt said earlier, 99% might not even be good enough depending on your environment. The other thing is that you need poses. So for robots, you're usually going to want to interact with something. In order to interact with something, you need good, accurate pose estimates of the objects. So for robotic perception, we might need to change the problem a little bit from what those other data sets are trying to expose to enable robust vision. So first, rather than trying to recognize kind of everything in the world, everything on the internet, we'll restrict the set of objects that we're going to work with, because a typical robot might work with maybe a few hundred or 1,000 objects or something. And we'll recognize instances instead of categories. So rather than kind of treating all soda cans as one label, we'll say a Coke can is one label and a Sprite can might be another label. And this kind of enables us to reliably estimate and verify poses. So on the existing data, there's promising results so far, but we really need to scale it up, the number of objects under consideration. So what we've done is set up a data collection rig here. And so there's these 5 high-resolution DSLRs on an arm. And on each camera, there's actually a Carmine mounted there to get RGBD images as well. And here is a computer-controlled turntable that we can rotate to within ½ degree. And while collecting data, we typically rotate it and stop every 3 degrees. So for one object, we can take high-res and RGBD images, 600 of them, in under 5 minutes. So the goal is really to get 2,000 plus objects. We're currently at 100. And again, we have 600 high-resolution images per object, 600 RGBD images per object. For each of those images, we have calibration information and segmentation masks for the object, and 3D models built for each object. And so if you're interested in working with the data, you should check out this website, rll.berkeley.edu/instance_recognition. And at the website, you can also suggest objects that might be useful for you in your own research. Thanks.
Our next presenter is Silvio Savarese from Stanford University.
Okay, so before I start, we'd like to thank students and researchers in my group, which contributed to the work I'm going to present next. So let me start with this image. So here we see two monsters, which look like identical in shape and size. And if I ask you what these monsters are doing, well, you might be a bit confused. You don't know what to say. You might be thinking they're just floating in this kind of empty space, right? So now let me put these monsters into this environment. So there's a long tunnel, and you might recognize this is the famous monster illusion. And now you can come up with a much more interesting story. So you can tell that you can tell there is actually a big monster on the back, which is chasing us after a small, tinier monster on the front. And even if you know that actually in the image, in the pixel space, these two monsters are identical. So clearly, the space is altering our perception of the objects and their geometrical properties. At the same time, objects is also affecting our perception of the space. Now we can tell that the height of this tunnel is as high as the farthest monster. So psychologists, and what I want to advocate here is that, perception, it's really an interplay between object and space, where objects are constrained by the 3D space, and the 3D space is shaped by these objects. And what I want to advocate in this talk today is the fact that modeling this interplay is critical for perception, for scene understanding. So psychologists has a long time advocated the importance of this interplay. In a number of seminal studies by Biederman and colleagues, it was shown that humans have learned the typical relationship between object and space. And these are typically described in terms of location, size, and support. And they've shown that when those relationships are evaluated, like in these two examples, so subjects were recognizing those objects much less accurately and much less efficiently than otherwise. So computer neuroscientists have also looked at this problem, and it's also recognized the importance of these integrations. And they've shown that from the V1, where low-level visual processing takes place, there are two main computational pathways: the both pathway to the ventral streams where objects are recognized, and the where pathway through the dorsal streams where the space is perceived. And they believe that these two pathways converge into an area called the prefrontal cortex, where object and space are understood in a joint fashion. So in vision, researchers have worked mostly in two main areas of research. One is reconstruction, one is recognition. And most of the time, these two problems have been handled in a separate way. So people either are trying to look at the problem of obtaining accurate metric reconstruction of the world, or extracting semantics. So what I advocate in this talk today is the fact that it is critical to solve these two problems in a joint fashion toward the goal of perceiving the world in a true 3D sense. And I'm going to describe three ingredients which I believe are critical for solving this problem, which is modeling objects and the ability to model objects and their 3D properties, the ability to model interactions among objects and the space, and also the ability to model the relationship of objects and space across different views. So let me start with the first ingredient. So what we want to do is not only recognize and detect objects in an image and describe them as bounding box, but also associate some geometrical properties, such as what's the distance of objects, what's the pose, what is the 3D extent. And what we do in my group is to propose models for recognizing objects, which allows us to capture the intrinsic multi-view properties of object categories. And what we propose is to describe objects as a collection of parts which capture diagnostic appearance information object category. And these parts are connected together into a graph structure where each graph captures the relative position of one part with respect to the other. And we have shown that it's possible to learn these parts, this relationship automatically from training data. So here are some examples. So here we want to detect, let's say, these objects, and we want to not only find the bounding box around the object, but also estimate the pose, so which is described here by these 3 parameters: azimuth, elevation, and distance, and also characterize the objects with their parts. So be able to estimate the parts in 3D from in this case a single image. So of course, these approaches don't work all the time. There are failure cases, like in this case. Here, this car was recognized as a shoes. But good thing is that the pose was correctly estimated. It was guessed in the right configuration. So what went wrong? Well, the problem here is that these objects, so these detectors are designed to work in isolation, so to only recognize one car by a time. And the problem is, if we are able to actually contextualize recognition in a space and with respect to other objects, now we could do much better job. So for instance, we can tell that this object is supposed to be supported by a plane and is supposed to be next to an hydrant, and now this can be a shoes anymore. It has to be something bigger than that. So this brings us to the second ingredient, so the ability to model the relationship between object and space, which plays a critical role for scene understanding. What we have investigated is a way for learning relationship between objects, which we call 3D geometrical phrases, which allows to encode the geometrical and semantic properties of groups of objects, which tend to co-occur in consistent spatial and semantic configurations. So these are examples of possible geometric phrases that we extract from those images. In this case, the objects are 2 sofas and 1 coffee table. And what we have shown is possible to learn those geometrical phrases, so to collect dictionary of geometric phrases from a large set of training data, and to do that automatically in a compact fashion, and also by making sure that those representations are view invariant. They are not function of specific viewpoint. So here I show you some examples. So given an image on the left, we are able to localize the objects and recover what is the corresponding geometric phrase which is able to describe this scene. And here we are able to solve the problem of object detections and layout estimation in a joint fashion. So now the ability to recognize the objects is contextualized with respect to the other objects, as well as with respect to the space where these objects live. You can see we're able to handle fairly complex cases like those very clustered scenes where chairs are confused with tables and so on and so forth. So a third ingredient I want to explore is the following. So so far we have looked at modeling the relationship of objects in space within the same view. But what happens if we have multiple views? So we are observing the scene from different viewpoints. So this can be the case where we have a camera moving around, or we have a sensor network which is observing the same scene from different vantage points. So what we looked here is way for modeling the relationship of scene elements across views. And what we introduce is a novel framework which we call semantic structural motion, where we essentially generalize the typical problem of 3D reconstruction, which can go under the name of structural motion or SLAM, depending on whether you see a static number of images or sparse number of images or a video sequence. So we generalize the concept of structural motion in the sense that traditional structural motion, in the traditional structural motion problem, the idea is to consider trying to find features matches across views and use those to recover the scene as a collection of 3 points, as well as also recovering the camera positions. What we do here is not only trying to solve this problem, but also inject semantics and be able to recognize the objects and find the relationship of the objects across views, and those for localizing the objects in a 3D space. And we want to do this in a joint fashion, in a coherent formulation. So here I'll show you some examples from a number of images observing the scene from different viewpoints. Not only we like to solve the standard recognition problem, segmentation and detection, but also localizing those objects in 3D. So doing what we can call the semantic reconstruction. So being able to actually localize these objects in 3D, localizing scene elements, as well as estimating the position of the observers. And notice that this is done from a number of views which are completely uncalibrated. We don't know anything about those views, and also there is no actual 3D information coming from the sensor. There is no, let's say, LiDAR or a Kinect sensor observing those scenes. This is another example here. We have a sparse number of views observing the scene, and here we see the corresponding semantic reconstructions. In conclusion, I want to emphasize the concept that it's critical to model the interplay between semantic and space for perception. And for more information, you're welcome to visit our webpage in Stanford. Thank you.
Thanks, Silvio. Our next presenter is Ryder Winck from Stanford University.
Okay, thank you very much. My name is Ryder Winck, and I'm going to talk today about time-delayed teleoperation for robots in outer space for satellite repair. And basically the goal is we have a robot up in geosynchronous orbit here, and we want to control that robot from a ground station on Earth about 35,000 kilometers away. And there's about a half-second time delay just due to the distance of getting communication to and from geosynchronous orbit. But then there's a multi-second delay just caused by the pre- and post-processing of the data. And since Oussama wanted to say that he could apply underwater robots to space, I'd like to throw in a little sound bite to say we could also apply this to robots underwater. So anyway, moving on. So our approach is essentially to have the human interact with a virtual model of the robot that's in outer space and of the environment. So you have the robot out in space, but the human sends commands both to a virtual robot and also to the real robot in space. And we update this model based off of feedback data. And today I'm just going to focus on our model of the environment and how we update that and give feedback to the operator. So the idea is we want to give both visual feedback and haptic feedback. And we've already talked a little bit about haptic feedback today. But in order to do that, we want to have objects in the environment that can move. So when an object is in free space, we'll take delayed data from that, the state of that object that we get from space that's delayed due to the distance and the processing. And we'll propagate that state forward in time and present that to the operator to remove the time delay for the operator. We'll take that predicted state and test that to see if we're in contact with the robot. If we're in contact, we switch our environment model to a local-only model that doesn't take in delayed feedback but runs only locally, so that we can do all the contact mechanics and stuff fast enough that we need to provide haptic feedback. So we'd use this as long as we're in contact. When we remove contact, we have to wait one delay cycle for our propagated model to converge again, and we switch back to our propagated model. So in this way, we're able to achieve good modeling of both free space motion of the environment and also contact events. So to test this, we did a little experiment. We did two tests, one where we were catching an object and another where we were pushing an object. And here you can see our test setup. You have an operator at a workstation with a haptic device and seeing our virtual environment. And we have kind of a poor man's air-bearing system here. We have this little pod that floats along on the floor. And we try to catch that here with this remote space robot. And we're collaborating with the BDML, Marc Cutkosky's lab, and using their bidirectional gripper that if you're really persistent you might notice that this is from his talk earlier. So we're using it to actually catch the pod. So just some results here. This is with 2 seconds of time delay. And you can see this is with no prediction of the environment. And I'm trying to catch the pod, and I'm totally unable to do it. If we add in our predictive feedback, if you watch my hand here on the joystick, you see I move before the pod actually gets there and I'm able to catch the pod. And just to show repeatability, we did tests with no robot or environmental prediction, with just predicting the motion of the robot, and then also with prediction of the environment. And you can see that with prediction of the environment, we're able to catch it 5 times out of 5, regardless of the time delay. Whereas with just robot prediction, our performance declines pretty rapidly, and even worse without any prediction. And here's just an example in 1 degree of freedom of actual prediction of the motion of the pod. So in terms of switching between these two environmental models that we're using, here you can see where we push the pod from a stationary position, so we're actually moving the robot up and pushing this pod. And so in this little gray area is when we're using this local-only model that contains contact mechanics and provides haptic feedback to the operator. And so we're predicting this motion, and then when the pod leaves the robot, there's no connection, we switch back to this propagated model. And you can see the same thing when the pod comes in and it's moving, and we contact it to stop it and push it away. We're able to switch to this local model seamlessly, predict the motion. It's not quite as good here for the stationary case, and then switch back to our propagated model to converge back accurately to prediction of the motion in free space. So thanks a lot for your time, and here's just some of the other collaborators on this project.
Thank you. Our next presenter is Theresa Lin from UC Berkeley.
Hi, I'm Theresa, and I work with Professor Borrelli on driver modeling, and more importantly, I'm more interested in just modeling a person in general and a complex task, but my application recently has been applied towards driving. And so I did not have this video before the talk this morning, but I decided to put it in because the Anki drive video, and I thought it would be really cool if we can teach it to do something like this, such as drifting. This is one of our autonomous vehicles that was able to perform this task because it was performing this optimal policy that was learned from an expert driver. Anyway, so back to my original topic. You've seen this diagram from an earlier talk today, and we have the vehicle group working on the controller. We have environment estimation, and there's also the driver modeling part. So that's what I'm going to be talking about today. And talking about drivers and in general. So what do we talk about when we say we're going to model the driver as a controller? On one level, we can say, okay, we're modeling the driver on a high-level kind of basis, and we're saying that we're modeling what the driver is trying to make on a discrete decision basis, such as maneuver-based, lane changing, or you want to do lane keeping. So you're taking environment, the model of the environment, curvature of the road, you have obstacles in front of you, you have other cars going, and you have your own vehicle states. You take all these information, and the driver makes a decision on whether I want to change lanes or not on a particular situation or highway. So you can do such estimations using hidden Markov models. You can use support vector machines, and you basically switch between different modes of operation, such as that diagram over there is just one simulation of a prediction on a model that was trained on data. So this is a high-level decision-making process. So after you have made a decision of the driver decides I want to change lanes, then he executes a lower level control, which he would manipulate the steering and the braking and the accelerator of the car in order to achieve this lane change maneuver or lane keeping maneuvers. So on a lower level, it's a continuous decisions making on the car is getting continuous feedback on the car, and you can just use very simple state feedbacks or switch systems in order to model this process. So you have on the diagram over there, that's a very well-used model. It's called a preview point model in lane keeping. It's basically you just minimize the error between the position of a car and the center of the lane, and also minimize the heading angle errors. Some more complicated driver models that we have tried to implement. On the left, we have a switch system, linear system model. Basically, we're saying that modeling the driver to be learning some sort of stored feedback map or feedback policy that he has learned over time. And then this is a very simple computation because it's just a affine system, and you can have different feedback policy laws in different modes of operation. So in the diagram, it's a two-mode kind of operation, and he learns two different feedback laws. And on the right there, you have a more complicated model because here we're saying that we're trying to model the driver as a predictive kind of controller. So you're saying the driver is taking some sort of he has a representation of the environment, and he has some kind of model of how the dynamics of the vehicle would propagate if he was to propagate a certain control input. So then he solves the optimal control problem, much like the model predictive controllers. So just two different ways, and then it's you kind of want to say, okay, when does the driver use the simple model? What does the driver use a more complicated model? He actually makes predictions. So that was just models that's taken from just information from the vehicle, and you basically just take all these vehicle states and steering angles, and you try to come up with an input-output relationship, and you come up with that black box in the middle. But what if we had more information on the driver? What if we can actually equip the driver with things such as the EMG sensor, which that's a picture taken from one of the papers that Professor David Cole did. He put these EMG sensors on the driver, and then he tried to basically, EMG sensors, EEG sensors. That's a CUFNAS from Stanford University, and also you can look at eye tracking information, which is kind of what the video I have here is a driver driving on curvature. And you can see his switching between looking ahead into the curvature of the road and registering what the environment is. That kind of goes towards a feed-forward model. He predicts that if he's going to go over there, and then when he has a more fine-tuned feedback model, he looks more closer to the more in front of his car, and you can see this miniature switching behavior where he looks at a gaze point and tracks it, and then it would just keep switching back and forth. So that's just basically using eye gaze information to further tell us what's going on. Okay, so I guess I'm running out of time. All right, thank you.
Thanks, Theresa. Our next presenter is Eitan Marder-Eppstein from hiDOF.
So my name is Eitan Marder-Eppstein, and I am president and founder of hiDOF. And for those of you who haven't heard of us, we're still a relatively new company. hiDOF is a consulting and contracting firm, and we work in robotics, automation, and related areas. And today I'd like to take a little bit of time to just sort of tell our story and talk about consulting a bit. I think we've heard a lot today from sort of product companies and from people in academia. And I think it's also useful to just sort of get a different perspective on how you might actually make a business in robotics. I know a lot of you are students thinking about what you might do after your academic time is through. And so I just wanted to present sort of a different model for how you might do it. So I'll start with a little bit of history. I'm going to show a picture of a robot that has come up over and over today. This is actually the PR2, or the Personal Robot 2. And I, along with my co-founders, worked on this robot way back when we were at Willow Garage. And at that time, Willow was really looking to push personal robotics forward, to sort of develop software that was new and novel in the space and kind of take this great leap in technology. And along the way, we built a bunch of tools that you're actually seeing today, things like PCL and ROS and OpenCV. OpenCV existed prior to Willow, but we sort of extended it. And we sort of proved these tools out by, programming our robot to do things. So I was part of a team that programmed the PR2 to fetch beer, and that was really, really exciting. And we got it to play pool, and we got it to do sort of all of these things. And I sort of found myself in this weird situation where I was asking myself, okay, so why? So what's the big deal here? We have a tool, and this is supposed to represent a tool that you might not know what to do with. And I found myself in this position where I'm wondering, okay, like we have this great tool set, we have all of these things that we can apply to all of these different problems, and I kept asking myself, well, but what's the problem? And so I found myself, along with a couple of my co-founders at Willow, sort of struggling to find a nail for our hammer, I guess, so to speak. And we spent a long time just exploring sort of different product trajectories that we might take. We all sort of had aspirations to start a company. And we had been told that the way you start a company in Silicon Valley is you find a product idea and you go out to many of the investors that are sort of around Silicon Valley and you raise a VC round, and then, you're good, you're golden, you're going to sort of take your shot. But that wasn't happening for me, and it was sort of frustrating at the time. I didn't really know what to do. Oh, Gary. Oh, okay. So anyway, I didn't really know what to do. I found myself in sort of this hard situation. But at that time, there were also people sort of coming to Willow Garage and saying, hey, we have this problem. And it may not be in robotics. It might be in an adjacent space. Sometimes it was in robotics. And they would say, can you help us solve this problem? And for the most part, Willow's response was, no, we're pushing personal robotics forward. That's our mission. We're not really in the business of sort of helping you solve like these niche problems. There were some exceptions to that. IPI got their start by sort of taking on one of these problems, actually. But it seems like there might be an opportunity there for me. And given that I didn't have any problems that I knew were sort of worth solving, I got together with sort of 2 other guys at Willow, and we decided to take the leap. We left Willow. We decided we were going to sort of solve some of these actual problems in the real world. We rented some office space, and we had absolutely no business, and it was awesome. But then over the last year or so, we actually did sort of enter the world, and we started to see sort of this wide range of new and interesting problems that our technology was applicable for. And we've taken a lot of time over the last year to just sort of get a high-level view of the space, of what's going on in robotics and adjacent spaces. We've worked on technologies in autonomy for vehicles. We've worked on big sort of industrial robots. We've worked on stuff in sort of mobility and perception. We've worked on things in warehousing and logistics, and that's sort of just scratching the surface. That's just in a year, and it's been sort of a wild year in that sense. But it does seem like there really are problems out there to be solved, and sometimes I think it's just hard to sort of put the people who have the technology together with the people who actually have the problems. And I guess I'm advocating that consulting is sort of a reasonable model sort of for that. And so along the way, we also sort of branched out into all of these spaces that I didn't originally think we would be in. So I sort of covered the range of spaces that we work in, but my initial thought was that we would leave Willow and we would be firmly in sort of industrial robotics and applying technology there. But it turns out that just robotics and a background in robotics is applicable to a way broader space. And I sort of started to think, okay, so what is it that we're doing? If it's not just purely robotics, like what is it that we're actually doing in the world? And it sort of occurred to me that all of the problems that we solve do have something in common. And I think it's really important for everyone in this room today, actually. So all of the problems that we solve sort of are on the edge of what's possible. They're just sort of trailing behind research. There's a research out there, and it seems like it might be possible. There's a wave of people like you who have done a lot of work to sort of prove out a space. And we are in the business of sort of trailing behind, staying in touch with academia, and sort of picking the pieces that we think are actually ready to bring back and transfer to something that looks like a product. And so the thing that we do, and our bread and butter really, is sort of this technology transfer operation. We, as a team, have backgrounds in academia. We're very connected to that community. And we sort of trail behind and just pick the pieces that we want, and we help our clients harden them. And I didn't realize, one, how hard that is as an operation, and two, actually how valuable it is in the real world. There's a lot of interest in doing sort of this technology transfer skill. So if you find yourself as, an academic who also has, I guess in our case it's the software engineering chops to back it up, but you could be a mechanical or electrical engineer as well, I think it is really, really valuable to be able to sort of come up to speed in a space very quickly and make sense of sort of the landscape and pick the pieces that you want for sort of your application area. And so that's basically, in a nutshell, kind of what we do. I'm going to take a little bit of time just to sort of make a shameless plug because it is a talk and I get to do that. So over the last year, we've grown from 3 people to 7. And we do sort of have a need for more people to help us in this endeavor. So if you find yourself thinking, hey, I'd really like to take some of my research or even research that I didn't even do and actually transfer it to the real world, to deploy it, to sort of actually see, the impact of what academic research can be, you should consider, I guess, us or any of the other companies in this room as well. And also, if you find yourself sort of with a product or a problem that you think is really hard to solve and you could use extra hands or extra expertise, we're a consulting organization, so we're around. I'm going to, I guess, let you go almost a minute and 40 seconds early, but thank you very much for the time, and feel free to ask me questions afterwards if you want.